Hello everyone and welcome to the pre-lab lecture video for lab number 12, experiment number 8, the concentration of a salt solution in Chem 100L. The objective of this experiment is to determine the mass of sodium chloride or salt in a salt solution. From the mass of the sodium chloride and the mass of the solution, you will be able to calculate the concentration of sodium chloride in the solution. Concentrations will be calculated in percent, parts per million, and parts per billion. So let's talk a little bit about water. If you acquire water through tap water or even thinking about seawater, this is not a pure sample of water. Instead, this is what we call a solution. And the reason why we call it a solution is because there are some solutes inside of the water, which could be considered the solvent. And we're going to go into those definitions more in a little bit. But we wanted to talk about, what is in water, like tap water or seawater. Well, there are ions in water, and you can see that some common ions that are found in either tap water, and then usually significantly more of it would be found in seawater, are cations like sodium ion, magnesium ion, and calcium and potassium ion, and some anions such as chloride ion and sulfate ion. So these ions are found in water, right? And you can see there's even a mention of the concentration. So these are measured in ppm, which stands for parts per million. And we're going to go into what that means in a little bit also. So let's start with some background information. First, when we say tap water and seawater is a solution, what does that mean? What is a solution? Well, a solution has to have at least one solute dispersed in the solvent. So for example, the solute is usually the substance present in lesser amount, right? And in this picture, it's the salt. The solvent is the substance present in greater amount, and in this picture, it's water. So because they're pouring salt into water, and it looks like they have a glass stirring rod, so they're probably going to stir it up, and eventually it will appear as if the salt disappeared, right? And some people think, well, the salt then went to a liquid phase, right? Maybe it melted into a liquid, but that's not the case, right? So the salt is not going to a liquid phase when it dissolves in water, right? Instead, it's becoming dispersed in the water as separate sodium ions and chloride ions. And once it's in there, we call the entire thing a solution. So what helps keep the sodium ions and the chloride ions in solution? Well, it's the attractions with the solvent, which is the water molecules. So ions on the surface of the crystal, so you can see these ones on the surface, they're labeled chloride, which is minus, and sodium are the purple balls, which is plus, right? So they dissolve in the water as the water molecules are attracted to the ions, and that attraction pulls those ions into solution, and the water surrounds them. So you can see that the partially negatively charged side of water, which is near the oxygen atom, is attracted to the positively charged sodium plus ions. And that attraction allows the water to pull this sodium ion away from the crystal. Instead, it's going to be now surrounded by oxygen atoms in the water because, again, that oxygen has a negative charge, the sodium has a positive charge, and they're forming a attraction. The same thing happens to dissolve the chloride ions. Those are negatively charged, and they are attracted to the partially positively charged part of water, which are the hydrogen atoms. These have a partial positive charge. Those are attracted to the negatively charged chloride ions, and this attraction helps pull the chloride ion away from the solid to get surrounded by water. Notice how the partially positive part of water is surrounding the negatively charged chloride ion. So eventually the solid crystal is pulled apart into its individual ions and surrounded by water molecules. And we say that when that happens, it's in solution. And we no longer see the solid crystal when it's in solution. So we're going to be talking and calculating solution concentrations. This is a core chemistry skill to be able to calculate a concentration. So at its most basic definition, the concentration of a solution is the amount of solute divided by the amount of solution. So the amount of solute and the amount of solution may be expressed in more than one unit. For example, amount could both be expressed in grams. We could talk about amount as a volume, so like liters of solution. We could talk about moles, right? And the moles of solute could be an amount. So there's various units that can be used. The first solution concentration calculation that we want to learn is to be able to calculate mass percent. And sometimes that's followed by m over m in parentheses. And that's just telling us that we want to use mass over mass in this calculation. So sometimes you might see m over v or v over v, where v would stand for volume. But in this case, we're going to be using the mass of the solute divided by the mass of the solution, right? So that's what the m over m stands for. So the mass percent is the mass of the solute over the entire mass of the solution, which is different from the mass of the solvent. For example, if we add 42 milliliters of solvent, which we're going to see in an example soon, that doesn't mean that there's 42 milliliters of solution because you haven't taken into account, right, the volume, or in this case, the mass of the solute, right? So the mass of the solute and the mass of the solvent combined become the mass of the solution. And because it's in percent, we're going to multiply by 100, and the units will be in percent. So let's say that we are going to be preparing a solution, and it's going to be a solution of potassium iodide in water. So we're going to start by weighing out 8.00 grams of potassium iodide. The potassium iodide is the solute. And then we're going to add 42 grams of water, and water is the solvent. So they weighed out their 8 grams of potassium iodide, and now they're adding 42 grams of water for a total of 50 grams. So this 50 grams is the mass of the solution, which includes both the solvent, the 42 grams of water, and the 8 grams of the solute, potassium iodide. So to calculate the mass percent, they take the 8.00 grams of, somehow this changed to potassium chloride when it was potassium iodide on the previous slide. Not sure how that happened, but we'll just pretend it's the same thing, okay, of the solute. And then the total mass of the solution, which we can see here is 50.00 grams, times 100, and we would report our answer to 3 significant figures because 8.00 is the minimum number of significant figures in our calculation. So we can report this as 16.0%. All right, let's talk about how we can use percentage as a conversion factor and other types of concentration units, right? In terms of parts per million and parts per billion and what that means. So first of all, we were just talking about percentages, such as the mass percent. We can actually write that as a conversion factor by just choosing a unit and expressing that unit in both the numerator and the denominator, right? So if we choose kilograms, we would use kilograms for both the numerator and the denominator, or grams could be both the numerator and the denominator, right? So we choose a unit and we express the percentage as a numerical relationship of the parts of this unit to 100 parts of the whole. So for example, if a problem says a person might have 18% body fat by mass, this tells us that 18%, and you're going to choose a unit, and it's talking about mass, so it would make sense to choose grams or kilograms. Because they're talking about a person, we might choose kilograms. So that means that they have 18 kilograms of body fat in 100 grams of body mass, right? So that's a conversion factor we can write for given the percentage of body fat that this person has. And because it's a conversion factor, right, we can interchange it, right? So we could put the 18 kilograms of body fat in the numerator or in the denominator, right? Since it's a relationship, right? And we're not changing anything. So it's like multiplying by 1. Okay, and make sure that you're using the correct number of significant figures because 18 has 2 significant figures, right? And the 100 kilograms is considered to be exact. Your answer should have 2 significant figures. So it's important to remember that if you're given a percentage, right, and it should usually tell you by what, like for example, by mass, right? We can then convert that by taking that percentage in a certain unit and dividing it by 100 of that same unit. And then for very, very small ratios, we use other units such as parts per million and parts per billion. We can go directly from a mass percent to parts per million or parts per billion just by changing the units in the numerator and denominator. For parts per million, we want the numerator to be in milligrams and the denominator to be in kilograms. This is just a convenient set of units that would give us parts per million, and we can use ppm as the unit. You can also do parts per billion by converting the mass units in the numerator to micrograms and the mass units in the denominator to kilograms. Right? So, for example, when we had our 18% body fat by mass, we wrote the conversion factor 18 kilograms of body fat in 100 kilograms of body mass. If we were wanting to convert that to, for example, parts per million, notice that the mass unit in the denominator is already in kilograms because it was in 100 kilograms of body mass. So all we would need to do is then convert the 18 kilograms in the numerator to milligrams. And if we wanted to express our number in parts per billion, we would convert the 18 kilograms in the numerator to micrograms. So again, these are typically used when we have very, very small ratios. There's very, very small amounts, something that might be measured in milligrams or micrograms, right, in a kilogram. All right, let's talk a little bit more about the actual experiment that we're going to be doing this week. So in the experiment, in your supplies, you're going to find 3 vials, and they're all going to have the same unknown letter. So if you see the picture here, there's 3 vials, all labeled unknown B. So you should have 3 vials, and they'll all be unknown A. They might be all unknown B or all unknown C. Whichever letter you get, make sure to record the unknown letter on your data sheet. It's very important that you record that, otherwise we won't know if your numbers are accurate or not. And then one at a time, we're going to take these solutions, these saltwater solutions or sodium chloride solutions, and we're going to put them in a 250 milliliter beaker. We're going to use our alcohol burner to boil off the water. You can also use your stove if you would like to do that. And what we're going to do is we're going to evaporate the water so that the salt residue is left behind, and the salt residue needs to be completely dry before you weigh it. So the picture has quite a bit of volume. You can see it's about like 170 milliliters or so. There's definitely not going to be 170 milliliters in each of your vials, right? So we're going to have a much smaller amount of liquid in the beaker, so don't be concerned about that. In addition, our solutions are colorless, right? So we're not expecting a blue color at all. So it's important that you understand that you're going to be, the reason why you're provided 3 vials is to do 3 individual trials. So you don't want to mix all 3 vials together and just do one evaporation. You want to evaporate them one at a time so that you have 3 sets of data or 3 trials so that you can average the amount of salt residue behind and hopefully end up with a more precise value as a result, right? So the salt residue is the solid residue that's left behind after the water, which is the solvent, is evaporated. So it should be a white crystalline solid. So this is what the data sheet looks like in the lab manual. I put a blue box in this first row, and that's because in the procedure it tells you that you don't actually have to measure the volume of the salt solution, because we're going to be measuring the mass of the salt solution, and we're going to be using that to calculate our mass percent, so we don't need the volume. So you can just go ahead and pour the vial directly into the beaker without measuring the volume of the solution. And then you're going to, but of course, before you pour the solution in, you want to weigh the beaker. And you can also use your evaporating dish instead of your beaker. So in this data table, it says evaporating dish. If you're using a beaker instead of the evaporating dish, that's totally fine. So you can use either one. Regardless of which one, you want to make sure you measure the mass of that beaker or evaporating dish when it's completely dry. Remember that when you're using your digital scale, all of the numbers on the scale are significant. So make sure you're recording all of these measurements to the nearest hundredth of a gram. Okay, so you're going to write the mass of the beaker or the evaporating dish right in the data table. You'll pour in the solution and then record the mass of the solution and the evaporating dish together. We're going to boil off the water and then measure the mass of the evaporating dish plus the solid salt residue. Make sure to include your units after each measurement, which should always be in grams. And then you can calculate the difference, right? So the mass of the evaporating dish plus the residue minus the mass of the evaporating dish gives you the mass of the residue. The mass of the solution can be calculated from the mass of the solution plus the evaporating dish minus the mass of the evaporating dish. Remember that when you're doing subtraction, you need to always be consistent with the number of places after the decimal. So for example, if your mass of your solution plus the evaporating dish is 146.50 grams, and the mass of your evaporating dish was 100.5 or let's say 0.30 grams. I don't want you to write 46.2 grams, right? For the mass of the solution, you need to write 46.20. Okay, so when you are subtracting values, if the last number is a 0 and the precision is to the hundredths place, you need to include that 0. That's really, really important. And a lot of you make that mistake and then mess up your significant figures. So again, if I was subtracting 146.50, so taking that and then subtracting 100.30, I would report 46.20, not 46.2 grams. So that's an important thing to remember, that with subtraction, we need to look at the number of places past the decimal and make sure that we're consistent with always recording to that place. Okay, some important things to remember when doing the experiment. Be careful with hot glass, or even if you're using the ceramic evaporating dish, be careful with that. Things that are hot, right, can burn you. So, and hot things look the same as cold things, right? So use your hot mitts or something that will protect your skin from hot glass if there's any chance that it could be hot, right? We're going to do 3 individual trials by evaporating the water in each of your samples one at a time, right? So you're basically doing this experiment in triplicate, and then eventually we will record the average of the data. We're going to be taking all mass measurements to the nearest hundredth of a gram. Make sure that when you're heating or boiling off the water, you don't overheat, because you don't want to cause splashing, right? If the water splashes out of the evaporating dish or the beaker, it will cause you to lose some of your solution, which will cause you to lose some of the salt, and then there'll be less salt residue at the end. And make sure not to weigh the salt residue until the salt that's left behind in your beaker or your evaporating dish is 100% dry. If there's any steam on the sides of the glass, if there's any water at all left behind, that's going to give you an erroneously high mass of salt, when it's really not the mass of salt, it's the mass of the water plus the salt. So you want to make sure it's completely dry before you take that final measurement of the salt residue and the beaker / evaporating dish. So after this, you're going to be calculating your first concentration, and we're going to start with calculating the mass percent. So the mass percent is calculated by taking the mass of the solute, right, which is your sodium chloride residue, divided by the mass of the solution. They need to be in the same units, and they will be because you've always been measuring in grams. Multiply by 100, and then that is your mass percent. The units are the percent symbol. Make sure that you're recording your mass percent to the correct number of significant figures. And you have to look at the significant figures in the mass of the solute and the mass of the solution to decide which is limiting, to see how many significant figures you should be reporting your mass percent to. Once you have 3 mass percents from your 3 trials, you can calculate an average by adding them up and dividing by 3, and then record that in the data table. Make sure you show one calculation in the space provided. Part C asks you to convert your concentration to parts per million and parts per billion. The units when calculating in parts per million are just written as ppm, all lowercase. Parts per billion would be ppb. And that's because the mass units cancel out, right? So we're just left with ppm. Well, really they don't cancel out because they're in different units, milligrams over kilogram or micrograms over kilogram, but we can just use parts per million instead of saying milligram over kilogram, etc. Okay, so again, you already have your mass percent, and you have the mass of the solute in grams and the mass of the solution in grams. So what you need to do is just convert the mass of the solute to either milligrams for parts per million or micrograms for parts per billion. You're also going to need to convert the mass of the solution, which you originally measured in grams, to kilograms. And I've included some useful conversions for you. It's important to know that there are 1,000 milligrams in a gram, that there are 1,000 grams in a kilogram, and that there are 1,000,000 micrograms in a gram. If you know those values, you'll be able to convert the grams of solute into either milligrams or micrograms, and the mass of the solution to kilograms. Once they're in the correct units, you don't have to multiply by 100. You just do the division, right, and write the number. You're going to be reporting these numbers in scientific notation into Canvas, and you just include the units, which are either ppm or ppb. All right, let's talk about the pre-lab for this experiment. So if you've been paying attention, you can define the unit ppm. So that's basically just asking you, what does that acronym ppm stand for? Define residue in context of this experiment. And you can list some common ions that might be found in tap water. Question number 4 says 150 milliliters of water is collected from a local lake. The water is weighed and evaporated to dryness. The data is shown below. Calculate the concentration of the residue in percent by mass, parts per million, and parts per billion. Show all your calculations for full credit. So again, I'm going to point out that it's really important to be careful of significant figures when subtracting. And we're going to run into that issue I was talking about earlier, where if you take 570.055 grams, which is the mass of the water sample in the beaker, and subtract the mass of the beaker, which is 420.025 grams, you're going to end up with a number in your calculator that appears to be only to the nearest hundredth. However, remember that the precision when subtracting is based on the number of places after the decimal. So because both of these two numbers have 3 places after the decimal, or are to the nearest thousandth of a gram, your answer after the subtraction needs to be to the same precision. So your answer will end in a 0 and be to the nearest thousandth of a gram. So be careful when you're doing that calculation, right, to report the mass of the water sample to the correct precision. Okay, so all of the data is given for you to calculate the mass of the residue in grams and the mass of the water sample, which is the solution, in grams. You can take the mass of the residue divided by the mass of the water sample times 100 to give your mass percent, and make sure to report to the correct number of significant figures. And then we just need to manipulate the units to calculate parts per million and parts per billion. This is given to you, the masses are given to you in grams, right? So we're going to have grams of residue initially over grams of solution. But remember, to calculate parts per million, you need milligrams of residue over kilograms of solution. So you need to do some dimensional analysis to convert your units and to convert your units in the numerator and the denominator, and then the final units will just be parts per million. For parts per billion, you need to calculate that grams of residue and change it into micrograms. And then change the denominator, which is grams of solution, to kilograms of solution. Do that division, and your units will be ppb, standing for parts per billion. For the post-lab questions, there's a series of questions asking about errors in what happens if there are certain errors in the experiment, right? So for example, if the residue was not heated to 100% dryness and the salt was still somewhat moist, how would that change the final amount of residue? And then the second question I think is a little bit tricky, but the way I read it is, if a large piece of dirt, say that weighs 10 milligrams, falls into the beaker just after the sample is evaporated to dryness and is weighed. So I read that as the dirt does not fall into the beaker until after the solution is evaporated to dryness and after it is weighed, right? So if something falls into your beaker after you've already weighed the beaker, right, then does that change the mass, right? So you can think about that. But that's the way I'm reading that question. And I made sure that the answer matches my expectation in Canvas. All right, and then the last question in the post lab says, if you calculated a saltwater solution of about 3.5%, what would be the molarity of this solution, right? And it gives us some additional information. It says, assume the density of the solution is 1.03 grams per milliliter. And it also gives you the molecular weights, also known as the molar mass, of sodium chloride, which is 58.44 grams per mole. So remember that when we have a mass percent, right, we can write that as 3.5, for example, grams of salt, which is the solute, right, over 100 grams, and that's considered an exact value, of the solution, which is the saltwater solution in this case. So I put this conversion factor table that we saw before when we were looking at somebody who had an 18% body fat, and how we were able to take that and express that as 18 kilograms of body fat over 100 kilograms of body mass. Remember that we can express the 3.5% of salt, right, in the saltwater solution also the same way. We're going to just pick our own units. So you could pick kilograms, right, for the mass of the salt and the mass of the saltwater solution, or you could pick grams, right? As long as they're the same unit, it doesn't matter because they would cancel out. So we can express that, right, as the amount of salt, right, in some unit, for example, grams of salt over 100 grams of the solution. So that's important because that's our starting point for this problem. So right now we have, for example, grams of salt over grams of solution. And it wants the molarity of the solution. Well, molarity is defined as the moles of solute divided by the liters of solution. So we need to get the numerator, which is currently in grams of the solute, which is sodium chloride, into moles of solute. Well, you know how to do that. You know how to convert grams to moles. We're going to use the molar mass, also known as the molecular weight, which was provided to us in the problem. So if we take that 3.5 grams of sodium chloride, divide it by the molar mass, 58.44 grams in 1 mole, we'll have the moles of sodium chloride. And then we'll be in the correct unit for the numerator. Currently, though, our denominator is in 100 grams of solution. But in order to be in the correct units for molarity, we need the denominator to be in liters of solution, not grams of solution. But we know that density relates mass and volume. So we're starting with our 100 grams of solution, and we can use the density, right, to convert to milliliters of solution. So we take our 100 grams of solution, divide by 103 grams per 1 milliliter. And then just remember that there are 1,000 milliliters in a liter. Make sure to use that to get to the final liters of solution in the denominator. Again, we're going to start with 3.5%, which can be expressed as 3.5 grams of sodium chloride over 100 grams of solution. We're going to use the molecular weight or / molar mass to get to moles of sodium chloride in the numerator. And then we're going to use the density followed by a milliliters to liters conversion to get from grams of solution to liters of solution. If we do that, we'll be in the correct units for molarity. So we can report that number, whatever number it is, right? And then the units will be capital M, which stands for molarity. So it could be like 1.0 molar, for example. That's how we would write that. So 1.0, and the unit would be capital M. So that's what we're trying to do for the post lab. All right, so that was the end of the pre-lab lecture video. I hope you guys have a great week.